The linear approximation is what we're going to continue this time. I wasn't sure if anybody was paying attention last time, so I'll give you a little refresher. This is the formula for the linear approximation, and this is called, so when you use this formula, this is the linear approximation to, it is approximation to or of, I don't know, I'm going to say of, sounds better to me. The linear approximation of f of x near or at x equal a. That's what you call this. The linear approximation of f of x near x equals a, or at x equals a. The idea behind this is f of x, you imagine, is some kind of weird function, and a is a specific value of this, or a specific point in the domain. Maybe I'll put it right here, let's say. And the way you, what the linear approximation represents, it represents the tangent line. It is the equation of a tangent line to this function here. So it's the line which goes through that function only at that point. All right, so in this picture, the f of x is this weird one, and the L is this line right here. All right? It is just the tangent line at the point x equals a. Why we call it something different, I mean, we call it the linear approximation, is because this line can be used to approximate the values of the original weird function. So this is useful to approximate f of x, which is a weird function, using only a line, which is not weird at all, right? The line is just a line. It's useful to approximate f of x, and it is a factor a, right? Overall, the line and the function may be quite different, but if you sort of zoom in near this point a, the line and the function look the same. That's the whole point of this. And you can use the line instead of the function if you want to estimate values. If for some reason the function is too hard to find the true values, you can use the line instead, all right? Last time around we used the linear approximation to estimate some square roots of things. This time we're going to do some similar kinds of things, only they won't all be square roots, but I thought let's warm up by estimating a square root again. So let's estimate, how about the square root of 27, all right? This is one way that you can try to compute the square root of 27 by hand. Obviously, you would need a calculator to get the value of that typically. But you can use a linear approximation to do pretty good without too much work. All right, so what we're going to do eventually is we will plug in L of 27, right? So we're going to use this formula up here. I'll just write it again. This formula you'll need to have memorized eventually. It's not that complicated. F of a plus f prime of a times x minus a, right? I hope yeah. Eventually, like at the very end, we're going to get the answer by plugging in L of 27, plugging in x equals 27 here. But we'll have to figure out what all the other stuff there is before we get to that. So we need to choose what we use for the function and also what we use for the specific point A. And this, there's, I suppose, some minimal amount of artistry here. You just have to think about what is the function that I'm trying to estimate some value of. I'm trying to estimate the square root of 27. I think of this as some value of the square root function, right? So my function that I'm using here is square root of x, which more conveniently, we pretty much always are going to write as x to the 1/2, all right? That's the function that I'm trying to find some value of. So that's what the f of x is. And then the a. So a is the specific point on the picture here. It's the specific point where you make the line meet up with the original function. But the way you choose the a is this should be some number or some point near 27, which we already know the square root of. Right? In this case, I'm trying to find a square root of 27. I don't know the square root of 27, but there is a number near 27 that I do know the square root of. What do you think? 25. Yeah, that's the only reasonable choice. I suppose you could go to 36, but that's further away, and the estimation will be not as good. So I'm going to go 25 here. All right? This also, I suppose you have to be slightly creative. I mean, you have to think a little bit and sort of invent a value for yourself, but it will usually be pretty obvious what you should be doing. Okay, and now I'm just going to plug everything into the formula that you see up top there. So throughout, I'm going to use A as 25. The F is the square root of whatever. So for example, F of A will be square root of 25, which is 5. So in the formula up here, I'm going to put a 5 right there. All right. X minus A will turn into X minus 25 because A is 25. The only, I mean, it's not really hard, but the hardest part, I suppose, is F prime of A. This means F prime of 25. In order to find F prime of 25, first we need to find F prime of X as a function. So for F prime of A, you find F prime of X first as a function and then plug in A, which is 25, right? So what is F prime of X? You have to take a derivative. Here's F of X, is X to the 1/2. So what's F prime of X? Somebody want to shout it out? 1/2 X to the minus 1/2. Great. So that's F prime of X, which means F prime of A, which is 25. F prime of 25 is 1/2 times 25 to the negative 1/2. Now, I would like to simplify that. I mean, the whole point of this problem is to do everything by hand. So can we simplify this as much as possible? What do you do with 25 to the negative 1/2? I'll leave the 1/2 like it is for now. 25 to the negative 1/2. 1/5. Yeah, how did you get that? Yeah, right. So this is really 25 to the negative power is really 1 over 25 to the 1/2, and 20 to the 1/2 is square root of 25, which is 5. So this is 1 over 2 times 1 over 5. 1/10. That's what F prime of A is, 1/10. All right, now we're going to just plug everything in. So the formula has disappeared already. I'll write it again. F of A plus F prime of A times X minus A, right? This F of A, we said up top, 5. Ooh. 5 plus F prime of A, I just said, is 1/10. X minus A. X is X. A is 25, right? We don't, sorry about that. We don't plug anything in for X because I'm trying to write the equation of a line here, right? So X should still be in there as a variable. And this is, it is now the equation of a line. It's in a weird format. You could rearrange it if you wanted to, although it's not really going to be helpful to do that in this example. All right. We're pretty much done here. Remember I said we are going to finish this problem off by plugging in X equals 27, right? That's going to be the final answer. So let's do it. L of 27 is 5 plus 1/10 times 27 minus 25. And what's that? This is 5 plus 1/10 times 2. 1/10 times 2 is 0.2, right? This is 5.2. Look at that. I'm doing decimals in my head here. 5.2, right? Or 5 2/10, however you like. This is apparently an approximation of the square root of 27. I plugged this into my calculator just to see how good it is. So I'll say, actually, square root of 27, the true value that I get when I plug this into my calculator, 5.1961, etc. So I feel pretty good about that. That's quite close to 5.2, which is what we just did by hand. All right. this is how you use the linear approximation to compute values of weird functions that you can't really otherwise do by hand. Any questions about that? I find it kind of satisfying to be able to do this by hand. I'm not sure why. I think the same kind of person who I make my own maple syrup. Did I tell you? I think I mentioned that, yeah. The same kind of person who makes maple syrup also likes to estimate square roots by hand, maybe. I don't know. All right. Any thoughts about that? I have a friend who used to be a prepper. Like he thought that civilization was going to end and he stockpiled like seeds in his basement. Maybe he would like computing square roots by hand too. I don't know. Probably not, knowing him. But he was prepared. Okay, I'm going to do one more example, which doesn't have to do with the square root. Like all the examples we've done so far have been about square roots. And then I got one for you all to try, and then we'll talk about something else. So let's try. This is a more geometric, I suppose. Use a linear approximation to estimate. I'm not going to tell you like a specific number. It's up to you to figure out the details here. I'm going to say use a linear approximation to estimate the surface area of a cube with side length 9. All right, so the cube here. And the length of each side is 9. Well, that's not what I meant. Sorry, I wrote something different on my paper. I might as well write the same. You could do this just as easily. Actually, what I want is, sorry, I'm going to erase this. With volume 9 is what I meant to say. So the side length here is not 9. I'm going to talk about the side length right quick, but the side length is not 9. The volume is 9. All right. Estimate the surface area of a cube which has volume 9. This one we have to do a little bit of preliminary work to even figure out what number we're supposed to be estimating here, right? Like the number that I'm referring to maybe is something like the square root of 8 or something like that. But we have to figure out what exactly is the surface area of a cube that has volume 9. Can we say, first of all, can we figure out what the side length is? So if the volume is 9, then the side length is, anybody, can you say what the length of one side is if the volume is 9? Not exactly a nice number here. It is the cube root of 9. Yeah, that's kind of what the cube root means. That's why it's called the cube root. The cube root of 9. Right? If you think, like if you call that x, then the volume would be x cubed. So we have x cubed is 9. And then x would be the cube root of 9, whatever that is. That's a weird number. That's the side length. What about the surface area? That's what I'm trying to ask here. The surface area of a cube. I don't know. Do people memorize? There's a formula for the surface area. I don't think that's a formula that you typically memorize. But the cube has 6 sides to it, and each of the sides has a certain area. Anyone? What do you think? Can you tell me what's the surface area will be? So the surface area is, I want to say something like 6 times, and then here the number, the area of each side, right? Because there are 6 sides in the cube. They all have the same area. What do you think? What would the area of one of the sides be? Area of each side. What do you think? Right? So length times width, yeah. So what would that be in this case? I think you can say kind of specifically. Like this side here, this is the cube root of 9, right? And it's a cube. That is, all the sides are the same. Yeah. You are squaring it. It's like it's not quite that what you said. It's really this. And these do not undo each other, but this is this cube root of 9, the whole thing squared. Just because one of these sides is the cube root of 9, and to get the area of the whole side, you square that. Because it's a square, right? And then you multiply by 6. That gives you the 6 sides in the cube. All right? Are we feeling this? I don't know if you're feeling this. This thing here you can write in a different way. So really the whole problem here is we need to estimate that number, right? We need to estimate 6 times the cube root of 9 squared, right? This actually you can write as like an exponent, 6 times 9 to some power. Anybody remember how to do this? I want to put an exponent up there. You know, a square root is a 1/2 power. This is a cube root, which is also squared. Anyone remember that? Yeah, this is the 2/3 power. Great. The cube root would be a 1/3 power, and then you're squaring it, so you get a 2/3 power. So this is 6 times 9 to the power 2/3. All right? So this was a lot of preliminary work to figure out exactly what is the number I'm trying to estimate. This is the number. Remember, like the first problem we did was easier. I just told you, find the square root of 27, right? This is the number you're supposed to find in this example. 6 times 9 to the 2/3, all right? So let's see if we can, go through the rest of the linear approximation. What you got to do is figure out some function, f of x, and then also some value a. That is a nearby value, which you already know how to find the answer for. In this case, what function am I going to use? You know, in the previous example, it was the square root of 27. The function was the square root function. So you have to look at that number there and ask yourself, like, what kind of function does this look like, which has a value plugged into it? I would say the function here, this 6, I don't mind multiplying things by 6. Really, the hard part is this thing, the 2/3 power, right? So I'm going to say my function is 6 times x to the 2/3. All right? That's the hard part of this function is the 2/3 power. So that it's 6 times x to the 2/3. And then I intend to plug in 9 to this to get the answer. And the a, all right, this is a little tricky also. I have to choose some value for which I actually do know how to find the 2/3 power. Something hopefully near 9. So this should be something near 9, which we know the 2/3 power of. Remember what the 2/3 power means? It means take the cube root and then square it. Of course, I know how to square anything. Really, the issue is the cube root. That's the hard part. Anybody know a number near 9, which you do know the cube root of? Yeah, 8. 8 is near 9, and we do know the cube root of 8 is, what is it? 2, yeah. So I'm going to choose a equals 8, all right? This is something that we do know how to find the 2/3 power. I don't know if I know that just offhand, but you could figure it out if you had to, right? That's the point. Okay? We are now set up to just sort of plug everything into the formula, right? The formula, remember, is L of x equals f of a plus f prime of a, x minus a, all right? Before we just start plugging things in, eventually we will need to use the derivative, so maybe I'll just, at this point, take the derivative, f prime of x. You do the thing with the power, right? The 2/3 comes down, multiplies onto the 6. 6 times 2/3, I believe, is 4. So this becomes 4x, and the new exponent will be negative 1/3, because I subtract 1 in the exponent. So that's f prime of x, all right? Let's see if we can plug everything in then. So I need f of a. This would be 6 times 8 to the 2/3, right? Remember, a is 8, and I plug that into f here. So this means 6 times cube root of 8 squared. The cube root of 8 is 2, so this is 6 times 2 squared. This is 6 times 4, which is 24. So eventually, when I plug that into my formula, that value is 24, all right? And we just got to work everything else out too. So that's what f of a is going to be. F prime of a, same business, but I use the f prime formula, which is here. And again, I plug in 8. So it says 4 times 8 to the negative 1/3. That's totally different from 2/3, but this also we can do. This is going to be 4 times 1 over 8 to the 1/3. 8 to the 1/3, it's the cube root of 8, which is 2. So this is 4 times 1 over 8 squared. Right? That's 64 in the bottom. 4 over 64. What? There should be no... What am I doing here? Sorry, this is... Anybody agree? This is bogus. 8 to the 1/3. Down there is 2. I wrote 8 to the 2. It's 2. Sorry about that. Simpler than that. 8 to the 1/3 is 2. So it's 4 times a half, which is 2. Sorry about that. All right, now we can just plug everything in. L of x is f of a first is 24, plus f prime of a is 2, and then x minus a was 8. So this is my formula for L of x. And then what do we do to finish it off? Yeah, we want to do L of 9. Remember, the point of this was we're trying to find this value at 9. We know what it is at 8. We're trying to do it at 9, so we plug in L of 9. So that means that 6 times, 9 to the 2/3. This is approximately equal to L of 9, which is 24 plus 2 times 9 minus 8. That's a 1 in there. I guess it's 26. Right? That's our answer. So that square, I guess, its surface area is approximately 26. And just to check my answer, you might as well do this if you have a calculator and you're doing the homework. You'll know if you did it right or wrong. The true value of 6 times 9 to the 2/3 is actually equal to 25.96 something. So close to 26. That's what I'm looking for. All right. This is how we do the linear approximation. That one, there was some tricky steps at the beginning. Any thoughts about that? I got something for you all to try. And then this will be the end of it. I would like for you to try estimate sine of 3 radians. All right. Sine, of course, is a very weird function to find values of, unless they are like the values that everybody knows about from the unit circle. Any other thing you plug in, you basically have to use a calculator. You can do this using a linear approximation. So estimate sine of 3 with the linear approximation. All right, see what you think. You should start by trying to choose the function f of x and the a, which is some number near 3 that you already know the sign of. See what you think. Did I mute it? I'll give you a couple more minutes and then we'll talk about it. All right, let's talk about them. I don't know if everybody finished. That's all right. So first of all, you need to choose the f of x and the a. So the f of x, I'm going to choose. You always sort of look at this thing and try to thinking of this as some function with a value plugged into it. I think the only function that makes sense to choose here would be sine of x. And then apparently you had sine of x and then you plugged the 3 into it. So I'm going to choose my function f of x to be sine of x. And the a is a number that's close to 3 in radians that you already know how to find the sine of. What did you think? Some number close to 3? I know a lot of you wrote it down. Shout it out. Pi, yeah. Say it proud. Pi. Pi is close to 3, and it is a number which you already know the sine of pi, or at least, you should know the sine of pi. You should be able to figure it out, right? Whenever you see things in radians, you should naturally think about multiples of pi, or things like pi over 2 or pi over 3 or something. And what is something in terms of pi's, which is close to 3? Well, pi is close to 3, so you might as well use pi exactly. Okay, great. Just because we're going to need it, I will also say the derivative, f prime of x, that's just cosine x. And I think we can plug everything in, right? This is a fairly straightforward one. We get f of a plus f prime of a, x minus a. That's the formula for the linear approximation. And we plug everything in. F of a will be sine of pi, plus f prime of a will be cosine of pi, and then times x minus pi, right? And the sine of pi and the cosine of pi, I hope you either have those memorized or maybe you think for a few seconds and figure out. Sine of pi is 0, and cosine of pi is -1. The way that I remember these is I have memorized the pictures of sine and cosine, where this is pi in the middle. This is sine, and cosine is this one, right? Where this is pi in the middle. So the sine of pi is 0, and the cosine of pi is -1. That's how I remember those, but if you have some other way, that's fine too. Well, anyway, I was in the middle of saying that this is the equation of the linear approximation. Actually, you could simplify all of that. It's just pi minus x, right? And so my final answer will be plugging in 3 to this function, L of x. So L of x is pi minus x. And so that means L of 3, which is my approximation of sine 3, will be pi minus 3. And that is about as good as this gets. I mean, a pi, I don't know how many digits of pi you know, 3.1415. So this, if you subtract 3, you just get that stuff, the decimal part of pi, right? So the sine of 3 radians is apparently close to that number. This is an approximation for the sine of 3 radians. All right? As I always do, I plugged that into my calculator. On the calculator, actually, the sine of 3, make sure you're using radians, is 0.1411 something something. So again, quite close to the actual value of the sine of 3. Right? Can I just say, are there any questions about that one? That's the end of this problem. What if instead of 3 radians, I had said 3 degrees? What about, what about sine of 3 degrees? I don't want to do the whole thing here, but what will be different? Yeah. Yeah, for the A, you really should not use pi anymore. I mean, pi doesn't even really make, the only reason you use pi here was so that I could do sine of pi radians is 0. Cosine of pi radians is -1. But if you're using degrees, the only sensible thing to use, so this time, use A equals 0, right? Because 3 degrees is very close to 0 degrees as far as the function goes, whereas 3 radians is not really close to 0 radians, right? 3 radians on this graph, 3 is like over here, close to the pi. Whereas on the corresponding graph using degrees, this would be 180, and 3 degrees is way over here, right? So you want to choose a nearby value in each case. In the first problem, using radians, 3 is very close to pi. Using degrees, though, 3 is close to 0. So I don't think we need to go through the details, but I just wanted to say, if you were using degrees instead, you would do the same stuff, but use 0 for the A instead of pi for the A. All right? Any more thoughts about that? This is the linear approximation. That's all I wanted to do for the linear approximation. I think we can move on to the next bit. All right? Excellent. Let's just cross the line here. Actually, that's the end of chapter 2 in the book. I don't know exactly how they decide to start and finish the chapters, but chapter 2 is all about the derivative, and that was the linear approximation was the last section in chapter 2, which was about the derivative. Chapter 3 is also about the derivative. I don't know why they just decided to go to a new chapter, but it's still about the derivative. What we're going to talk about for the next couple times, this is like a major topic, is about maximum and minimum values of a function. I imagine you probably did not do the linear approximation in high school, even if you did some calculus. Well, if you did some calculus in high school, you probably did talk about this stuff. Maximum and minimum values. It's a big deal in calculus. This actually was the original type of problem that calculus was invented to solve, to find the maximum and minimum values of functions. It is useful in many, many different scenarios in the real world. Anyway, if I draw, say, what I mean by that, probably you already know what I mean by that, but if I'm going to draw just like a piece of a function here that sort of doesn't go on forever, but it just sort of has an end to it. has two ends to it, like that. All right, here is a function. I suppose the domain of this function is only from here to here, right? It doesn't go all the way across the real line. It's only that much of the function. But anyway, when I see a graph of a function, it's very easy, if you know what you're looking for, to tell me about the maximum and the minimum values. And there's kind of two types. This right here is the maximum value of this function. So when I say maximum value, I mean the maximum y value that the function ever achieves. And the fancy word for that is, this is the absolute maximum of that function. And I'll say in a moment why the word absolute is used there. This is the absolute maximum. It is the single point on there which has the greatest y value of all. There is also an absolute minimum here. That is a point which has the lowest down y value at all. And in this example, it would be this point on the end here. This is the absolute minimum. All right? That's the point on the graph which has the lowest y value of all. There's also this point right here, which probably you feel like is some kind of a minimum point, although it is not the lowest overall because there are many points over here which are lower down, but it is still important. This point here is still important. This is called a local minimum. Some books use the word relative minimum, but our book says local, so we're going to say local. This is a local minimum point. What that means is it's the lowest value of all the nearby ones. All the points near here are higher up. But it's not absolutely the lowest because these ones over here are even lower. So this is the difference between absolute versus local. All right? And for similar reasons, this point on the end here, it is a maximum of the nearby points, but it's not maximum overall. So this is a local maximum. All right, a local maximum. So let me just, I'll try and write in words here. The absolute maximum means, there's a slight technicality here. It means some point where the y value is greater or equal to all other y values. The technicality is right here, greater or equal. That usually doesn't come up, but it is technically possible to have two separate points which are both the absolute maximum because they're like a tie. So if there's a tie, it still counts as an absolute maximum. They have to share the title between more than one point. That can happen. Typically that doesn't happen, but absolute maximum means some point where the y value is greater or equal to all the other y values. And the minimum is some point where the y value is lesser or equal to all the other y values. All right, those are absolute maximum and minimum. Can I tell you a little story about absolute maximum and minimum points? This is interesting. I found this interesting. I learned a few years ago when I went hiking with my kids. We went to the tallest mountain peak in the state of Connecticut. Are you ready for this? This is a little conundrum you can tell your friends at dinner. We went to the tallest mountain peak in the state of Connecticut. It's not very tall. And I looked it up when I got home, and I learned that this place where we went, the tallest mountain peak in Connecticut, is not the tallest point in Connecticut. Think about that. Tell your friends at dinner. This is a true fact. The tallest mountain peak in Connecticut is not the tallest point in Connecticut. Anybody have some idea of why this is true? And I'll tell you, this is not some kind of stupid thing about there's like a big tower somewhere. The answer is totally ordinary, not stupid at all. About there's like a tree somewhere, no funny business. Anybody, how can it be true that the tallest point in Connecticut is actually higher than the tallest mountain peak? It is true. Hmm?
It's where the Like you can, maybe it's a small mountain.
It is a small mountain.
Maybe say the mountain begins at sea level and goes up. It's the biggest mountain and therefore the tallest mountain peak, but a smaller mountain starts at a higher elevation.
Yeah, it's nothing like that. I mean, really, the elevation of the top of the mountain peak is not the highest elevation in the whole state. Do you have another idea? How could it be higher though than the floating island somewhere? Yeah, something like that. I don't. The highest mountain peak is below sea level? No, it's not that. Don't all mountains begin below sea level? I don't know. Yeah, nothing like that. I think she was onto something, although I don't quite understand. It has to do with, this is a true fact, there is land elsewhere in the state that's higher than the highest mountain peak. It's just that land elsewhere sort of has no peaks to it. So is that even possible? It is possible. Maybe we'll come back to this. Within the next 30 minutes, I think we'll have a better perspective on this. Maybe. I don't know. If we don't, I'll... anybody have another idea before I just move on? You can continue to think about this in the back of your mind. There's nothing like... This is not a trick question. Yeah? Yeah, it's nothing like that. That I would consider a stupid trick question. There's not any... No nonsense. It has to do, so here's a hint, and I'll tell you the answer at the end. It has to do with the fact that a mountain peak is always a local maximum, like a point like this. Now, this one on this picture is also an absolute maximum. What I'm telling you is that the mountain peak, which is automatically a local maximum, in the state of Connecticut, the highest local maximum is not an absolute maximum. There is elsewhere in the state a higher point than the highest peak. Yes, he's got it. It's at the border. So here's a true story. If you looked at the elevations in Connecticut, there's a place, I believe it occurs on the border with New York. So here's Connecticut, here's New York. The tallest peak is like here, right? And then it does this. There's another peak just over the state line. And so this is the tallest mountain peak in Connecticut, but the actual tallest point in Connecticut is right there on the border. Yes. Tell your friends. Yeah. I actually saw, like a very popular YouTube video called The Highest Point in Every State. And it was like this sort of young, attractive hiker bro who went to the highest point in every state. And I was like, oh, I'm waiting for this guy to get to Connecticut where he's just like on some road somewhere. Like there's nothing remarkable about the highest point in Connecticut. It just is some point that happens to be on the border somewhere. But he was at the tallest mountain peak in Connecticut. And I was like, no, bro, like that's not that, like it has a better view there, but it's not actually the highest mountain peak in Connecticut. All right, anyway, yeah, this is an important distinction between absolute and local maximum, right? This is a local maximum point. The absolute occurs over here, not at any mountain peak, just at some random point on the border. All right, great. Thank you for engaging with my interesting conundrum. Let me give you the true, I want to write this as sort of a formal definition here. So for a function with a domain I hope that brief story illustrates like exactly where you consider the domain is actually important in matters of maximum and minimum values. Like the only reason that this weird thing about Connecticut is possible is because somehow Connecticut has like an end to its domain, right? There's an end to it. If for somehow the state of Connecticut went on forever, then that situation would be impossible. Like it is a fact that the tallest point by elevation on the entire Earth, it is actually the tallest mountain peak. Because there's no like border of the Earth which you could go up to and get some weird situation like this. So you have to focus on the domain in problems like this. If you're not considering what exactly the domain is, then you'll get wrong answers sometimes. Anyway, for a function with domain D, here's a definition about what exactly absolute and local minimum and maximum points are. I'm going to say f of c is an absolute maximum if f of c is greater than or equal to f of x. I'll write this better here. Greater or equal to f of x for every x in the domain. All right? So f of c is the absolute maximum point. It means it's bigger than all of the other points in the domain. Greater or equal, all right? And absolute minimum, can I just say like this? The only difference, the absolute minimum, if f of c is less than or equal to f of x for every x in the domain, all right? The absolute maximum is bigger than everything else. The minimum is lesser than everything else. And then what about local? I might as well write that here also. So f of c is a local maximum. This means it's bigger than all the nearby values, but not necessarily every value in the entire domain. So I'm going to say if f of c greater than f of x, greater or equal to f of x, for all x near c, all right? And local minimum means the same, but with the less than sign. If f of c less than or equal to f of x for all x near c. All right? This is absolute and local. Automatically, if you believe this definition, it automatically means that every absolute maximum or minimum is automatically a local maximum or minimum. Right. If it's absolute means it's bigger than everything, that means automatically it is bigger than all the nearby ones. All right. So every absolute maximum is a local maximum, but the other way is not necessarily true. There can be a local maximum that is not an absolute maximum. All right. These just more terminology here. Any maximum or minimum point or value, I should say. I just want to be consistent with my language. Any maximum or minimum value is called extreme value. So this is just an umbrella term. Whenever I want to talk about all the maximums and all the minimums, these are called altogether, they're called the extreme values, the ones, the biggest and the smallest, all right? Extreme value, or the singular, this is a weird word, but we use it sometimes. Extremum. It's like maximum, minimum, extremum. It means it's either a maximum or a minimum. All right. The word is extremum. The plural would be extrema, just like the plural of maximum is maxima. All right. Okay, this is the terminology. I hope everybody is clear on the meaning of all of these things. These are very easy to identify on graphs. For example, I drew that one. I just want to draw several pictures here and see if we can look at the graph and say, can you tell me where the extrema points are? the maximum or minimum, be they local or absolute. You basically want to look, here I'm considering the entire domain to be, all the real numbers. There's no boundary values. You basically want to look at all the kind of peaks, mountain peaks, and also these points here. So this one I would say is a local maximum. This is a local minimum. That's because this one here is smaller in its y value. It is lower down than the nearby points. This in its y value is higher up than the nearby points. This one over here is also a local maximum. In fact, this one is higher than all the points across the whole thing. So this is actually an absolute maximum. These are easy to identify on the picture if you know what you're talking about. Is there an absolute minimum on this function? The answer is no, because it just goes down forever on the two ends. That means there is no absolute minimum here. All right, because it continues to go down forever, so there is no bottom y value. All right. Great. More simple examples here. How about a function everybody knows and loves, sine of x, right? Are there any, local or absolute maximum or minimum points? You should be looking, for the local at least, you should be looking at all the sort of mountain peaks and the valleys. So they would be here, there's many of them, right? So this, if I were to, and the ones, up here, these are maximum points. These are local maximum. So we have a local maximum. Actually, I can say at pi over 2 plus, I'll write it like 2 pi n, right? This kind of thing. Pi over 2 is the first of those peaks, and then it repeats every 2 pi radians as you go across the picture, you get another one. All right, a local maximum. Is there an absolute maximum? Yeah. Yeah, I would say they all are absolute maxima, if I'm using the correct grammatical plural there. Yeah. Remember, if there's a tie, it still counts as an absolute maximum. So actually, we have a local max here. Actually, these are all absolute maximum. All right. And similarly, the ones down there, they are all absolute minimum points. And they're also local minimum points. So local min at, those I would write as 3 pi over 2 plus 2 pi n. And these are all absolute minimum also. Right? Great. I have maybe some slightly more interesting pictures. I don't know. How about the absolute value function? Right? The absolute value function, of course, comes to a sharp point there and then goes up forever over here. It seems to me something is important about this point. What would you call that point? Is it anything? Yeah? Yeah, I believe that's an absolute minimum point. So this point right here, x equals 0, is an absolute minimum. It's also a local minimum. Like I said, every absolute extreme point is automatically a local extreme point. Is there an absolute maximum anywhere? No, because the thing goes up forever on the two ends. There's no top to it, right? So x equals 0 is an absolute minimum. There is no absolute maximum. All right, great. Here is, how about, a very simple example, how about a line like this? What would you say about the extreme values for this one? I see some people shaking their heads sadly. There are no extreme values here. No maximum or minimum points at all, local or otherwise. This has no extreme values at all. Veils? No extreme values. Right? I think maybe that'll do for my pictures of examples. You want to hear another strange story about extreme values? This is I went a few years ago to a conference in Beijing, and part of there was a day off during the conference when it was a math conference, and we all went to the Great Wall of China, which goes kind of close to Beijing. It's like an hour away, and this is a place in the Great Wall where it like goes over some mountain ridges, and we had a tour guide, he was young, probably like college student age from Beijing, spoke English very well, and he was our tour guide at the Great Wall. And we could ask him questions about anything. And one question I asked him, I grew up like in New England, sort of in the shadow of the Appalachian Trail. I used to go to the Appalachian Trail with my dad, and this is like a 3,000 mile long trail that some people hike the whole thing. I never did anything like that. But I asked this kid at the Great Wall, is there anybody who ever like walked the whole length of the Great Wall? And he was like, "You stupid American." He said, "No, you couldn't possibly, like the Great Wall is way too long for that." And I said, like, "What? Okay, I know it's really long, but like people walk really long things, I think this was like my like white American attitude. It's like if I see a big thing, I'm like, I want to do that thing, the whole thing, right? That's like my natural response. And he said, no, like where would you even sleep? And I said, well, like you could have a tent. And he's like, where would you get your food? And I was like, I don't know, you could get food, I guess. He said, no, that's ridiculous. I guess this is like apparently not a Chinese cultural kind of thing to try to do the whole Great. I looked it up later. People have walked the whole distance of the Great Wall, but I think the first people to do it were like white people who were like, yeah, I'm going to do that. But anyway, this is not about extreme. I also asked this guy, because we were like going over a mountain ridge on the wall. I asked him, are we right now like near the highest point of the Great Wall? And he said, like, what? I think he had already decided that I was a stupid American, just asking stupid questions. And he was like, what are you even talking about? And I said, like, well, like the highest, like we're in the mountains right now. Is this the highest that the wall goes? And he said, how could you ever even, it doesn't even make any sense what you're asking. He's like, what do you mean the highest? Like the highest that the wall goes from the ground? And I said, no, I mean like the highest, measured to the ocean, from the sea level, the highest point along the wall. And he's like, no, you can't. He said, like there are some points are higher or lower, but there's no highest. And I went back and forth with this kid, like trying to convince him, like, yeah, I think there has to be a highest. And really it comes down to the fact that, like, the domain where the Great Wall exists doesn't go on forever, right? And all of my mathematician friends were standing there, sort of laughing at me, trying to explain about the existence of absolute maximum. Like it has to have a highest point somewhere. I was never able to explain to this kid. That's my other story about absolute maximum values. I must say, I have the greatest respect for this kid and his expertise about the Great Wall. I probably shouldn't have tried so hard to convince him because I ended up feeling foolish. And I think he ended up with the impression that like I really was just a complete idiot for trying to argue this with him. Ever since I've been telling myself, I must have been right when I was talking to him. I looked it up afterwards. There is a highest point on the Great Wall, and it was not near where we were. It was somewhere else. It was highest. All right. Anyway, we've got 10 more minutes. I'll just say a few more things about extreme values, why we care about extreme values. People care all the time. So finding both absolute and local extreme values is super useful in the real world. I said before, this was actually the original purpose that calculus was invented for, like the original problem that Isaac Newton tried to solve using calculus. Finding extreme values is super important. Like any kind of question, like say, I throw a rock, how high does it go? This question is about a maximum, an absolute maximum, right? You throw something up and you want to know what's the maximum height that is achieved, the absolute maximum, all right? That's a question about maximum, or something like in a business situation, and I'm trying to decide what prices I want to set, like what pricing will maximize my profits, right? This is what people are always trying to figure out. This, of course, is about finding a maximum value of something, or you want to like minimize your costs. That's about finding a minimum value of something. Many, many important problems in the real world, at some level, boil down to find the biggest or find the smallest, right? Those that I just said are really about absolute, although oftentimes the local extrema are just as important. For example, if you're like a investor in a stock market or something, and if you're like, let's say the value of your stock or whatever does this, which they do, right? They go up and down. What I just drew there has many local extreme points. Some of them are absolute, but actually to an investor, the absolutes don't matter so much as the locals. For example, the local maximum points are here, and here, and here, and here, and here, and here, right? Those are all maximum. And the local minimum points, I'll mark them in blue. I don't know if you can tell the difference. They would be here, and here, and here, and here, and here. Those are the minimum points. If any hotshot investors out there, what's the typical investment strategy when it comes to points like this? If you know that this is how the stock is going to go, the standard investment strategy is buy low, sell high, right? And every time in a real market, every time there's a difference like this, you can make money by either buying or selling. So really, if you think about it, we want to buy at all the local minimum points, and we sell at all the local maximum points, right? That way you make money both ways, right? So in the real world of investing, all these sort of like investment, they're trying to predict what's going to happen to prices, and in particular, what they care about ultimately is the relative or the local maximum and minimum points. If you can totally predict these, then you'll be able to make money every time. Of course, in the real world, nobody can totally predict the way these things are going to go, which is why that's the whole game to it, right? I think so. What we want to get into is specific techniques for actually finding. So we're going to learn methods to find the absolute and local extrema. It turns out the absolute are a little bit easier, so we're going to do those first, and then we'll talk about the locals after that. And I think rather than try and get started, maybe we'll just leave it at that. That's all right, everybody. Next time, we'll start about finding the absolute minimum and maximum. See you then.